today we are going to do section 4.3, page 369, partial derivatives. Now the partial derivatives are defined in the middle of the page. Let's see what it is. It is defined at this very familiar limit, okay? First, let's look at partial f over partial x. What is that? It's the limit as h approaches 0 of f of x plus h and y minus f of x and y over h. Now what is that? That is exactly the derivative of f of x if you ignore y, because y isn't changing. Y is just along for the ride. So it's simply the derivative of x, the same derivative we've been doing all along. Now to look at that in a picture, let's look at this picture that I got from way back in page in a book, page 346. Okay. Now look at this. There are two things. Now the partial derivative is same as the trace. You remember what the trace is? The trace is the line where the graph intersects the y equal to something over here. Okay, let's first look at the y case. Let me make it bigger. Come on. Okay. Move over. It doesn't want to move over. Fine. Anyway, so let's look at this, right? Now, you notice that along the line y equal to 0, the graph, which is that colored thing, makes a line with a y equal to 0. That's in the y equal to 0 plane. So the partial derivative is the regular derivative of that line, okay, at any different point. It's a derivative, and so the partial derivative is basically we're going back to doing derivatives, okay? It just because y is held at 0. Y is held constant, but y value can be any value, right? For example, see that y equals to pi over 4, and that gives you a different trace. And the different trace, then your partial derivative will be different, but the idea is the same, okay? So the partial derivative is the exact same thing that we've been doing in the past. And then that's partial x. What about partial y? Same diff. Now, I think this is partial y, right? I think. Well, anyway, the point is partial y is when x is held constant. Let's say x is at 0. Okay, see the x equal to 0 plane there? It intersects the graph, and along you create some red line. And the partial derivative with respect to y is the derivative of that particular line. That, in other words, the partial derivatives of x or y one-dimensional derivatives exactly the same as we did in the past. The only difference now is that we're holding the other variable constant. And so then the whole thing, we're just considering the line now and not the plane or the surface anymore. So that is the definition. Therefore, we're going to be taking derivatives. Now let's look at example 4.14. So how do you take partial derivatives? What you do is you take derivatives as you always do, but you consider the other variable that you're not taking derivatives with constant. Okay, that's just, in other words, it comes along for the ride like 2 or 5 or pi, anything. It doesn't change. It doesn't do anything for the purpose of our taking partial derivative. And so with that, let's turn to the page. What example is this? 4.14. Okay, you notice that your book wants you to go back to the good old definition like we did in Calculus 1 in the beginning, before we figured out how to take derivatives for sure. Okay, this is the blunt force way of calculating a limit. Okay, then let's skip that. We are not going to write that much stuff down. Okay, and then the next, so that what we're going to do is simply just look at it and pretend that the other variable doesn't matter. And it's just a constant, and treat it like 1 and crank it out like real quickly. All right. So that's what we're going to do. We're going to skip this example and move on to the next example. Now, the next example then says, see, in the next example, the book decided that it got itself worn out doing everything by hand, the derivatives by the limit definition. Are you kidding me? And now you have so many variables and it's all blowing your mind. So instead, we are going to take partial derivative the regular way. Okay, let's see. We have, all right, now let's look at this, the next example, 4.15. Now that's much better. You have f of x, xy equal to that pile of stuff, right? What is partial f by partial x? I can tell you right now just by staring at it. Remember, y is a constant for doing this. So therefore it's 2x, right, minus 3y, and then minus 4. That's it. The 2y squared derivative of that is just 0 because 2y squared is a constant. Okay, so I got 2x minus 3y minus 4, right? Just like I said, piece of cake. And well, of course, that's an easy example. Derivatives can get more complicated, of course, but not much more, okay? Not unless you start doing the basic limit definition, then you're going to wear yourself out. So anyway, please do example 4.15 as part of your homework. Next, let's skip forward to page 374, where we have the partial derivatives. Now we have more stuff, okay? Now the more stuff, so now you have derivative of a partial derivative of xyz. And what's however, the principle does not change. Everything holds the same. That is, when you take derivative with x, see, y and z, or anything else, if you got more, w, etc., it doesn't matter how many functions are. Every single thing else sits around and do nothing. Okay, they just come along for the ride. And you take derivative of each function as if everything else is a constant. And then the same with partial f of partial y, etc., is all the same. Okay, you just hold everything else constant and take derivative, and that's your answer. That is what it means. And to see how that works, please do example 4.17 as part of your homework. And then again 4.18. And don't do the limit way, okay? I mean, that's like so primitive. Just go ahead and take the derivative. Let's not do the limit. I mean, look at what your book did. It took the limit of something and wrote out something this long. And check this. It's not necessary, okay? The derivative of something like that is a piece of cake. It comes out, you can even do it in your head, basically. So let's skip that part and just get to the answer, and then we're good. And that is example 4.17 and 18. Next, let's consider higher order derivatives. That is, if you can take partial derivative of x, you can do it again, right? And just keep doing it until something. So there is the higher order partial derivatives means exactly what you might think. For example, the partial squared x f over partial x squared is you take the partial derivative after you take the partial derivative of f with x, and so on. And then you notice that because we have more than one variable, sometimes you can take the partial derivative. Look at the second term right here, where you have the xy. What that means is you take the derivative of y first, and then you take the partial derivative of x. See? So then you have two of them. Or you can flip that around. And you can do the x first and then the y second, and so on. And then, of course, you can do y both times. And so then you have, so unlike the first order, unlike the first dimensional stuff, now we have mixes. You can do partial x, partial y, and partial y, partial x. As it happens that partial x, partial y happens to be equal to partial y, partial x if things are in proper conditions, like nothing is broken or gone to infinity, stuff like that. But anyway, so that kind of helps a little bit. But as you can see, we're looking at, a lot of grunt work. So please do that as calculating partial derivatives. Please do example 4.19 as part of your homework. It's tedious, but very straightforward. You just keep doing derivatives like you did in Calculus 1, and then you'll get to the end as long as you give yourself enough time and patience. So let's move on. And the next thing is there's a theorem 4.5, which repeats what I just said, is under certain ideal conditions, which means they're continuous, okay? That is, if fxy and fyx are continuous, then fxy equal to fyx, that is the mixed partials, what they call it, is are the same, which is convenient. But we're not going to prove that. And so we're going to move on. That's just something you can remember, because that sometimes saves you the effort of doing x, y, and then yx again, as long as you know the function is reasonable. And so next, we are going to talk about something called partial differential equations. Partial differential equations are the same as the regular differential equations that we had in Calculus 2. What that means is that you'll have a bunch of derivative stuff that happens to be equal, and you have to solve for it. Now that sounds like very, very hard, right? And it is, okay? Partial differential equations in my day are called particularly difficult equations or something like that. Anyway, so for example, you have a partial differential equation where you have ut equals to uxx plus uyy, and you have to somehow dig out some u that fits all that stuff. Now, we're not going to be doing that at this stage. We're just going to be given the answer, and then you take all the partial derivatives to confirm that the partial differential equation does work out. And that's what we are going to be doing. So again, you're just going to be confirming the answer. We're not going to do actually solving some partial differential equation right now. So with that, so please do example 4.20 as part of your homework. We have come to the end of this section, which is a quite short one, and where we were just going to be doing it's the same stuff we did back in Calculus 1. So please do homework for section 4.3 on page 386, problems 121, 27, 33, 39, 47, 50, 55, and 57. And I won't be talking about it too much, but just remember that a partial derivative just means, okay, recall what it means. It means you hold the rest of the variables constant, okay, and stash a plane there, and then you end up with some curve. And the curve is what you're taking the derivative of. That is, you're calculating the slope of that particular curve that your graph makes with a plane. And you might wonder, why do we want to know that? Then because it eventually helps you calculate the tangent plane. Okay, in one dimension we did the tangent line, right? In 2 dimensions we're going to do the tangent plane in the next section. Now the next question you might have is, well, but what if there are a whole bunch of variables? You know, they're partial. There's not just x, y. This is the x, y situation. But what if you have z and w and so on? Then what does it mean? By then we don't care. Okay, it just you can't draw it, so we don't care what it is. Even though you don't know what it is or can't see it, you can still take the derivative by holding all the other variables at constant. It doesn't matter if you have 1,000 of them, okay? And you can do the same thing. The process doesn't change. So you don't have to visualize it. In advanced mathematics, a lot of times you cannot visualize because we can't see things in more than 3 dimensions. But just because you can't see it doesn't mean you can't work with it or get it to come out, calculate exactly what it's supposed to be. So with that, please go do your homework. I won't be talking about it because the homework is just doing derivatives. So after that, we'll go to the next section. But I do want to mention something, is problem 85 in the previous section. That is, what page is that? Which is on is on page 366. The reason you have to do that right now is because I forgot I assigned it in the previous section. So please do that, and then when you're done, I want to talk about it. Now, now that you're done with trying to do problem 85, you might have trouble trying to figure out what the limit is. The reason is because what happens to do this kind of limit? Now, notice that, well, for problem 81, which I didn't assign, but you can do it very quickly. You just factor it, cancel something out, and then what's left is perfectly legit, and that becomes 0. Same as problem 83, which I did assign. And again, you cancel something out, and you are left with something simple, and then it goes to 0. But this thing, you can't cancel anything. I was beating it around and cannot cancel it. The reason is because this thing, the limit doesn't exist. Now, the way you can prove it is that if you hold y as 0 and z equal to 0, because everything is going to 0 anyway, so you make those things already equal to 0. Okay, and then you calculate what happens as x goes to 0. Now, in that case, if y and z are both 0, as you can see, x goes to 1. I mean, the whole function goes to 1, right, as x goes to 0. Whereas if you hold something else 0, that is, if you hold x equal to 0 and z equal to 0, and let y go to 0, then you notice the limit becomes -1, because y and the y here has two different signs. So then the limit goes to -1, which means the limit approaches two different things, which means the limit does not exist. And that's how to do that particular problem. That's a more interesting problem that I missed in the previous section. I wasn't paying attention, didn't think of it. But after I did the following section, then I suddenly remembered I better go find something like that for you to do. And so here it is.